Thanks for coming to our talk. Today we are going to talk about a system that we built to solve a specific business problem that we faced. It's called Epiphany. And one of the technical points of this talk is we had to deal with a lot of, connect a lot of events from one stream and a lot of events from another stream, and we'll get to the details. That's what made this interesting. I'll be joined in this talk with Shahanshad. He will start speaking a few slides later. We are a company that work in the area of online advertising. And before we get to the details of the business problem that we're trying to solve with this work, let's quickly take a look at the online advertising ecosystem in a nutshell so that we understand what's going on. In a way, just like any other system, like a networking system or a system, we are essentially a system that is trying to have a group of entities, advertisers in this case, trying to communicate effectively with another group of entities, the users, their potential customers, and both these entities are at the top layer, and the underlying infrastructure is somehow trying to support a communication paradigm between them. The goal of this communication paradigm, the businesses are trying to essentially find potential customers. So they are trying to serve impressions to potential customers. And if the underlying system does a good job of finding these customers who are just visiting online websites or such other properties on the web, then they will be interested in the advertisement. They'll be clicking on the advertisement and they'll get to the landing page. And once they get on the landing page, if we really did a good job, which we want to, they will convert. And this is a standard parlance in advertising terminology. Conversion is supposed to be something that happens after a few pages after somebody gets to the landing page. They go and buy something like a pizza, or they go and sign up for an email list or something like that. And essentially, this is what is measured by the advertisers as the success story. So if by showing, if we can show less number of impressions and still manage to get higher number of good quality conversions, that is what is considered success for us. As you can see that there are some key players in the underlying ecosystem. There's a physical layer, which is the advertising exchanges providing the communication, and publishers are providing the content to the users and drawing the users to the scenario. And Rocket Fuel is providing services to the advertisers that makes it easier for the advertisers to find the right users at the right time for the right ad. There are some companies, we call them observers, or that essentially work with the advertisers, and these companies are working with industry standard algorithms and giving advertisers a view into all the events that are happening on their web properties that helps them solve a particular problem. And this problem is called attribution. The word attribution basically means when at the end of a particular set of events, a conversion happens, the question that arises in the mind of all the players involved in the communication is what were the good events that led to the attribution, what were the not so good events that led to the conversion, and what were the not so interesting events that led to the conversion. And if we know the answer to that question, and if we can somehow drive agreement on the answer to that question across all players, then we will have a better chance of providing value to our customers. Here's a timeline of what I was trying to describe verbally just a while back. Essentially, a sequence of advertisements are displayed to the user on multiple different devices by multiple different companies. And this sequence is essentially, every one of the elements of this sequence, every advertisement is called an impression in advertising parlance. So think of this as a list of impressions followed by a conversion. Some of these impressions are from Rocket Fuel, some of these impressions are not from Rocket Fuel. Some of these impressions are on display devices, some of these impressions are on mobile devices. The goal of the exercise is to get better at identifying the effect of every impression across every different device during the customer's journey. And downstream, the result of having a good attribution platform is going to be felt by other teams, not just inside the company, but also outside the company. Almost everybody derives good value by having good attribution algorithms. At the end of the day, we can figure out using attribution what revenue comes back to us. Because if we showed the impression that led to the conversion, then we have some right on the revenue generated by the conversion. Also, if we can train better models, because the right impressions generate the right conversions, then we improve our probability of success in deriving these success stories. Industry classically has been using something called last touch attribution, where something very simple used to happen, and every participant in the game, they used to think that the last impression I showed to this particular user was the impression that led to the success of this conversion. While that is easy to calculate, it is also easy to see that no single player, only one company, the actual company that showed the last impression, only knows the right answer. Everybody else is deluding themselves. And also there are multiple different impressions being shown to the user. So it's probably not a good idea to, practically speaking, to give the entire credit to the last impression. Slightly more modern way of thinking about things, which is now more possible because of big data becoming more and more real and easier to do, is that technically we have multiple impressions on multiple devices, all feeding into some logical data storage somewhere. And these impressions, some of these could be from our company, some of these could be from other companies, some of these could be on different devices. At the end of the day, if we could somehow figure out, the second line is what is the view that we have. As you can see, we don't have the information that display at 2 and display at 3 were impressions shown by some other company. Based on just what information we have, if we could somehow figure out that we'll give 20% of the credit to display ad 1 and 60% of the credit to display ad 4, somehow we can derive better answers from this. And even more interesting is if we can have a platform where multiple algorithms could be computed in parallel, and for each of the algorithms we can come up with a different distribution of the weightage, then we can derive further downstream computational scenarios. So reporting can use one of the algorithms to calculate their revenue numbers. Modeling can use another algorithm to calculate what works best for the specific campaign. These are all good things. So the goal of the Epiphany platform is to provide a system where some of these things can be done in parallel. One thing that makes this problem a little bit more complex, remember a few slides earlier, I talked about the observer companies that are working with the customers and observing all the impressions and all the conversions that's happening. These are the only companies, along with the final advertiser customers, who have access to all the information. They know all the blues and the grays. They have all their pixels at every one of the places. So sometimes these companies use industry standard algorithms and give us granular, aggregated and granular conversion information as daily uploads. Now, in our Epiphany attribution system, we want to be able to consume these daily reports and treat that as just another algorithm in our system, just like we had multiple algorithms over here. If only we could treat the attribution information coming from external parties as another algorithm, then we could derive the same values downstream like we used to with the other algorithms. So what are some of the challenges and requirements from the Epiphany system? First of all, this is the overall architecture that we want to drive. The rest of the talk will focus on this orange-colored black box called rocket fuel attribution, while this slide is telling you what is the paradigm in which this black box operates. Essentially, the inputs to this black box is, number one, the history of impressions that we have served to a particular user. Number two, the current day streaming conversion data that we are getting from our web properties. And number three, the previous day advertiser data uploads that we have received from the advertisers. And combining all these three, plus all the algorithms set into our system by our data analysts, we want to run our attribution engine. And as a result of the attribution, what we want to populate are two Hive tables containing the same data. We call this the action table. And the first version is the action table partitioned by impression day. And the second version is action table partitioned by conversion day. It's obviously, the partitioning is done differently so that people with different objectives and interests could look at the table, query the table using different clauses and efficiently do so. The reason why we want them in Hive tables is because at the root of our culture, we believe in data democracy so very strongly. So we want downstream engineering teams and groups to be able to consume the data from Hive, aggregate it at whatever layer they need to, and upload that data to wherever that data needs to be consumed. One very interesting scenario that we wanted to support is the concept of reattribution. So sometimes what happens is that a particular new algorithm is considered, and we want to run that algorithm on impressions and conversions data that's already there in our system, that has already been attributed. We want to do a reattribution run and add the results just for this new algorithm based on the new information that has been received. This is the architecture diagram. As I mentioned, for current day's conversion data, we need to support real-time attribution, and for batch and re-attribution needs, we need to support batch. So whatever platform we come up with, whatever infrastructure we come up with, has to work without any changes on both our batch and real-time computation paradigms. And what is the complexity of all of this thing? If you look at it, the order of complexity, first of all, we are looking at the number of conversions, which is running into hundreds of millions per day. For every one of the conversions, we may have to look back at like past 14 days, 20 days, 90 days of data, and that runs into tens of billions of impressions. Thousands of advertiser reports are coming in every day from different advertisers, and hundreds of algorithms in the system. Sometimes the same algorithm can be manifested in different ways, like different number of look back days for impressions and things like that. As you can see that there's a multiplicative effect over here, and it is very difficult to just try to put this all in a Hive join and expect to get answers out. The Hive query will never finish, which is why we had to solve this problem. And I would like to invite Shahanshad to take over from here.
Hello, everyone. So now we would like to take a look at Epiphany, which is Rocket Fuel's attribution engine, attribution platform. Anirban already explained the general problem of attribution. We would like to make it more concrete and try to solve it. So at the heart of attribution, we are working with two different data sets. One is a set of impressions and the set of actions. Impression table contains the history of all the impressions that we served in the past. It will have columns like user ID, campaign ID, ad instance ID, which is unique ID for each row inside the table. And then you also have the timestamp, which is the time at which we actually served the impression. And the action table contains number of conversions and also the time at which the conversion individually happened. To give a concrete example, if you were browsing the internet and we showed you an ad about Pizza Hut, then there will be a record inside the impression table indicating that this event happened. And if consequently you went to their website and bought a pizza, there will be a record inside action table. What we want to do with the attribution is to come up with a different data set, which is essentially, we will call it attributed actions, which is for each row in actions table, you want to join it to append information about the relevant impressions to it. We will try to simulate a very simple attribution algorithm here, which is saying that we will give equal weight to all eligible impressions. And we define eligibility as saying that the conversion should have happened after the impression was served. Like if you already bought your pizza and you're watching Hulu or something, and then we showed you an ad about Pizza Hut, it doesn't count, it doesn't matter, it didn't influence you at all. So the last record in the impression table is not eligible because it happened after the timestamp of the conversion. Another requirement is that they need to belong to the same campaign. For instance, if you showed an ad about Pizza Hut and then you went ahead and bought a Domino's pizza, it doesn't count. We were right about that you want a pizza, but we didn't drive any value for the customer, hence we don't get any credit. So what we want to do is that for the given record, we want to associate it with the 2 existing records in the impression table and produce the output. So you could sort of think of it as a Hive query. You can possibly write a Hive query to produce this table, but the problem here is that the impression table has around 50 billion rows that you have to consider, and if you write a normal Hive join to do it, your query will probably never finish, and even if you finish it, it will probably be after the campaign has entered, and it's not useful anymore. So the problem here is essentially the search span. Like, you're looking at all records inside impression, and that's not feasible. Like, you should be more intelligent about the set that you are interested in. So the solution that we have is that we took the impression table and made it an H-based table, which is point lookupable, and we made the user ID as the key. So when we look at the action record, what we do is that we first look at the H-based table with the user ID B, and then you get the list of 4 records, which is not the 50 billion. You only have the 4 records now. And then you can do the attribution fairly easily. So if you want to make impression table, which already has 50 billion data points, a H-based table, you can do that. You can go ahead and implement it using your primitive H-based APIs. But if you're inside Rocket Fuel, we have already built something called Blackbird collections, which is an abstraction on top of HBase. It makes working with HBase a lot easier for us. So using Blackbird collection and a very well-tuned HBase instance, we are able to do this lookup in milliseconds. So if you are able to do the lookup in milliseconds, then the problem of computing this attributed action becomes very easy. A record comes in, you do a lookup in milliseconds, and then you produce the output. It's as simple as that. So another data set that we want to work with in case of attribution is the external advertiser data. Anirban already mentioned that we don't have access to all the touch points which exist, but advertisers do, and they might be willing to share it with us. And if they are able to share it with us, we might be able to use that and derive more value for the customer in the future. And the advertiser data format typically looks something like this. They have the user ID campaign at a timestamp of the conversion and the ad instance IDs to which they think that the credit belongs. The timestamp here is the timestamp of the conversion. In our earlier example, it is the timestamp at which the guy got the pizza. But since it is 2 independent systems recording the time, there will be a small difference because the event will happen at different time for the different observers, and there will be a difference. Also, sometimes because of technical reasons or limitations of based on law and things like that, the timestamp will have much lower granularity. Sometimes they just give us the date and nothing more. We can still do the attribution, like most of the people won't convert twice on the same day, for instance. Like, you wouldn't buy 2 pizzas at the same time. Maybe you do, but very rare that something like that would happen. So if we already have enough information to do the attribution there, even if that is the case. So what we want to do here is that given this attribution data from advertiser, we want to find the corresponding record from the actions table. If you look at it, the advertiser is talking about a conversion which happened around 10:12, which is the time, and we have a conversion record which is recorded at 10:11, which is off by 1 minute, and that's expected. So we would like to join these 2 records and put the extra additional information that advertiser is giving us right now and append it to the already existing attributed action table. The attributed action table already has the Rocket Fuel data because you would get the advertiser data very late. So you cannot wait for producing Rocket Fuel data up until that time. So you produce your Rocket Fuel data, and at a later time, you try to append this additional information. So how do you generate this attributed action? The problem is nearly very close to what we had before. If you try to do a normal join, it becomes complex because of 2 reasons. One is that the number of records that you work with is very large. Secondly, the join condition is no longer an EQ join, it's a fuzzy join. You have to match a prefix and things like that. And when you write a Hive query like that, it's possible for the join to explode. You have to be very careful when doing that. So the solution is very similar to what we did before. We took the actions table, and then we made an HBase table grouped by user ID, and then if you look for a given user, you'll get a reasonably small data set that you can work with and produce the output. So the first problem was of selecting the data that you want, and then you can solve that using HBase, where you pivot it as an HBase table, and then you're able to do it. Now the second problem still remains about updating the existing attributed action, which is in Hive table. How do you go ahead and update an existing Hive table? So earlier I mentioned that you can do a lookup on the HBase table using the key, and then you get the list of all records, and then you can do a linear search on it and figure out which is the conversion action that the advertiser is talking about. It turns out that you can actually make it much more efficient. Instead of doing a linear search, you can actually find the record very easily. In case of HBase, there's a feature where you can search for a row with a substring of the key. It doesn't have to be a prefix, it can be a substring, and it will efficiently do it for you. So instead of asking the table, give me the all record for the given user, you can say something like, give me the record for this user belonging to this day, provided that you have encoded your timestamp in somewhere in the key. So if you're clever about how you set your key for the table, you will be able to do it much faster. Now, traditionally, you wouldn't be very impressed by it. Like, if you have an array list of 10 elements or 100 elements, what's the difference? It nearly takes the same amount of time to process. But here, since you're reading from an HBase instance, which is an RPC request, if you can reduce the size of the data that you're reading and the size of the data that the HBase has to scan to find your answer, it becomes much more efficient. The HBase becomes much more responsive. So it actually makes a big difference to do this. So the second problem is that of point updates to Hive. So the advertiser data is coming at a different rate. Like some advertiser will give you data for yesterday, some will give you 1 week back, and many different advertisers behave in different ways. So you have to, whenever this data comes in, you have to go and update in Hive table, which is, Hive table is a very big Hive table, and then you have some rows in there that you want to update. So doing this is very inefficient if you depend on Hive to do it. It's not going to work out. You'll have to rewrite large amount of data just to update small set of it. So the solution that we came up with was to actually, instead of producing the Hive table directly, we create 2 intermediate HBase tables, and then we roll out the updates to these 2 HBase tables instantaneously. Whenever a new record comes in, we'll update these 2 tables. And when we notice that a consumer is interested in accessing this new information, we will pull the intermediate table into Hive, and that's a reasonably fast process. It only takes around half an hour to produce 1 Hive partition. And we only do it when there's a need for doing it. We don't always do it. Whenever there's a new data, we don't do it. So how do you do that? So we already have data sitting inside this first table, HBase table, which is the action keyed by user ID. We need that anyways to address the case of advertiser data. So we have data currently sitting inside this first HBase table, and our objective is to create these 2 Hive tables, which is a rearrangement of the data which already exists. And we created these 2 HBase tables to act as proxies. So when a change happens to the action keyed by user ID, which is an update to an existing row there, we will make the corresponding changes to these 2 intermediate HBase table. And periodically, we will pull it into the Hive table. That's the architecture. So the first question is that you have data sitting inside the action keyed by user ID table. That is the data which was written by that Epiphany driver itself. Now you want to make those same records. You have to take the record from the first table and put it into this other 2 tables based on whatever is the structure of these 2 Hive tables, right? So if you have an HBase table, what you can do is that you can ask the HBase table to give me the list, all the records which changed since some specific timestamp. We have a job which continuously runs to transfer data from one table to the others. So the first thing that this job does when it comes alive is to do a timestamp-based scan on the first table to give all the record which changed since it last ran. So using this timestamp-based scan, it knows the records which changed. Now what we need to find out is that for the records which changed, what was the old state of these records? It turns out that it is not sufficient to have just the new state of the records in some cases. So you do a point reads on one of the HBase table, and then you know what is the older state of the records. When you have the old state and the new state, you can figure out what are the exact changes that you need to make to the other Hive tables and then do that. So one thing that you have to notice here is that you have to be careful about is that you're writing a MapReduce job, which is essentially writing to HBase table. Traditionally, when you write a MapReduce job, you are working with an exactly one semantics, because if an attempt failed, HBase doesn't commit its result, so you don't have to care about what happened there. But in case of you're writing it in HBase and one of the attempts failed, whatever data it wrote earlier is still remaining in the HBase. So unless you have idempotency at the record level, right? If you process the same record twice, it doesn't really matter much. Unless you have that, you won't have correctness. So in all the schemas should be such that if you process record twice, it is okay for the system to do that. You essentially have to work with at least one semantics, not exactly one semantics. So far we have data pushed up into one of the intermediate HBase table, and the task is to pull an Hive table. Most of the time, the Hive table will be partitioned by some column. In our case, it's normally the date. So we will keep data for a given day inside one Hive partition. And normally you would be interested in pulling one specific partition of Hive, not the entire table. So the thing that you have to look for here is that when you're trying to pull one particular partition of Hive, you don't want to scan the entire HBase table. HBase table would have data for like 90 days. So you don't want to scan the entire thing. You have to be more efficient about which section of the HBase you are going against. The first thing that we do as part of this job is to actually create a snapshot of the HBase table. If you're writing a MapReduce on top of an HBase table and you're going to scan significant amount of data in the HBase table, it's always better to go against a snapshot. It improves your performance a lot. It also sort of preserves the cache on top of HBase. So overall, it's good for the HBase that you go through a snapshot. And then it's a MapReduce job. It will partition the records based on the partition column and then write in its file to the HDFS. So how do we make the scan efficient? Like if you want to pull a particular day, how do you prevent it from scanning everything? So the way that we do is that if you structure your row key in a specific format, you can do that efficiently. Our row keys are split into 3 parts. One is the hash part, and then the second is the partition column. That's the same as the column that you want the Hive table to be partitioned on. And the rest of the key is there so that you don't merge 2 records accidentally. And as I said, you can ask HBase to search for a given substring of the row key, and then it will give those records very efficiently. So if you have row key as part of the partition column, if the partition column is part of the row key at a specific byte location, you can look for those records very efficiently. The hash is needed so that not all records for a given day goes to the same region server. If you set the partition column as the prefix, what would happen is that on any given day, you will be writing to one region server with a lot of data, and then you're not anymore working with a distributed system. It's a single machine. So it's important to have a hash part in the key. Okay. So this is sort of Epiphany architecture. We did talk about most of the pieces. The one thing we left out was the line going from Epiphany driver directly to Vertica. This is essentially for the real-time pipeline. For real-time pipeline, we also, from within Epiphany driver, emit a Kafka topic, which eventually gets aggregated and displayed in the Vertica, which is a MySQL-like DB, very quickly so that you have real-time numbers very fast. We run Epiphany inside 2 mode. Either we run it under Storm or Hadoop. If you notice, the entire piece of the architecture is based on gets and puts and things like that, and you can do that either in Storm or inside MapReduce, both works. We normally run under Storm. When there is advertiser data or we want to reattribute an old day, what we do is that we run it under Hadoop as a MapReduce job. So once you build the system like Epiphany, the next thing is to make sure that it's running all the time. One of the requirements for Epiphany is that it needs to be a platform where anyone inside the company is able to come in and contribute a new algorithm. And most of the time, this new algorithm will be of experimental nature, and you don't want on one experiment to take down your production systems. So it's become very important to test any new releases that you make. So we depend upon a canary mechanism where essentially you have the code that you're trying to release. We already know the code which is okay. We run both of them in parallel and see, like, is one guy messing up with the correctness or the performance of the system. HBase has this nice feature. One problem with generally running Canary is that you have to copy a lot of state. You want both the systems to run in parallel, but without affecting each other. So you have to copy the entire state over to the parallel pipeline before you can run it. And HBase makes it very easy. Traditionally, you would have to copy a lot of data, but if you're using HBase, you can create a new table Y as a copy of table X, and they will share the common data, but any update that you make in the future to one of these two tables won't affect the other. They are independent table backed by a large set of common data. So creating these tables for the running the Canary becomes very fast. It doesn't take too much time. Another thing to notice is that HBase is not as HBase is a lot more fragile than your MapReduce or Hive, things like that. If you're not careful about your access patterns, you can bring your HBase instance down. So you have to be a little bit careful there. Another thing is that you have to make sure that you're using write-ahead logs on your HBase. What happens is that you write a MapReduce job, and the MapReduce will make a put request to the HBase instance, and the MapReduce will say that I did my job, and then it will say that everything is well and good. But if you didn't enable write-ahead log on your HBase, what could happen is that between the time that you finish successfully and the HBase flushing its data to disk, it could die, and then you would have data loss. And every other system would think that it has done the attribution, it's doing fine, whereas you wouldn't find the data later on. So why do all of this? Why does Epiphany help at all? Like what's the benefit of Epiphany for Rocket Fuel? So using Epiphany, we are able to support a lot of attribution algorithms at the same time. We can run different variations of attribution at the same time and see which one is doing better and which one is doing not so well and things like that. Also, we are able to allow experiments on attribution much more faster. Earlier, if modeling or someone comes up with a new attribution algorithm, to test it, you will have to run it for, like you will merge the code change today, and then you will wait for 15 days when the algorithm will run, and then you will have the new data, and then you will see, like, is it better or not. So essentially, the loop for testing something was very large. But using Epiphany, since every component inside is scalable, you can just, you have the new algorithm, we'll reattribute old dates, like 15 days or whatever, what we want, and then you will have the data in 4 hours to see whether it did make a difference or not. It helps that inside Rocket Fuel, all our HBase instances are provisioned on top of Yarn. So when we want to do the backfill, we'll need larger capacity for HBase that short period, right? So we'll just make a config change and then have the larger HBase instance for that time period and then run the entire attribution with it. So it becomes much faster for the modeling team to experiment with things. Also, it makes accessing the data much more easier. Inside the company, we are seeing a trend where we are moving for the processes, moving from Hive tables into HBase tables, because you can easily find your data. You can zero down on the data that you're interested in much faster. So as part of Epiphany, we are exposing the data as HBase tables as well, where hopefully in the future, people will be able to consume data to produce much more real-time pipelines. So that is from us. If you have any questions, we would like to take them now. The question was that how do we uniquely identify a user?
Yes, this is technology that we have been using. I mean, it's a very standard thing called cookie matching. All advertising exchanges in real-time bidding expect us to do cookie matching. It is determined by device or cookie.
And then we have also, on top of that, we have built algorithms which will try to club these different devices belonging to different same user. There are many ways to do that.
That is the clustering algorithm. We have done significant work in that area.
Thank you.
Thank you. Oh, question one. Okay, so you need a structured data structure. You need a data structure to store that. We use protobufs,
and the protobuf flows through the entire system. And in the Hive table also, they normally reside as protobuf. But then you have built a suite of UDFs which will help you slice through these protobuf and extract data. We tried a way in which we kept these data structures as primitive Hive structures, and it turned out that accessing these structures which are stored as Hive inside other systems, like if you're writing a MapReduce to run on this table where you're directly accessing the data, not going through Hive, it becomes much harder. So it turned out that storing it as protobuf and giving them UDF was the easiest way out.
And the algorithms themselves are stored as Java classes and parameters stored in a DB.
So you first run the attribution and let the modeling team run this UDF on the...
If they want to look at the data, yes, then they will use this UDF to get the data out. You can, if you're writing a Java class, if your model algorithms are Java classes, then you can just look at the protobuf directly. But if you're working inside Hive, then you have to use the UDFs. Okay, thank you.
Thank you.
Okay,